Everyone, thank you very much for joining us today. I know it's the last presentation of the day, and every one of you have got your fill of exercise after that walk from the Dolphin all the way out here. So we really appreciate you taking the time and the effort to get out this far to join us for this presentation. It's the fourth year that Josh and I have done this presentation, and every year we do it a little bit different to bring a little more value to you guys involving these topics that are so important to everybody in the SolidWorks community. Because I think we all realize that to every one of us, one of our main limiting factors in our design process tends to be our computer, our hardware, our environment that we're modeling in. We tend to wait on our machine too much, and we want to avoid that. We want to get our machines to the point that they are waiting on us. They're so fast that we can't keep up with them. And we're hoping to take you guys a step in that direction. This time we're going to do it a little bit differently than we did last year. We're going to employ a scoreboard to measure our hardware changes as we go forward through the presentation. Okay? Everything we do has been tested and retested to the nth degree. We made a lot of changes in hardware, in modeling environment, in modeling methodologies to figure out what changes are going to make the most impact to you, the users. Okay? Go ahead.
All right, so our agenda for today. First, we're going to talk about our objectives, why we're doing the presentation. We'll then get into the setup as far as what we did to set up all of our testing. Talk about the results. It's going to be broken up into two sections. Adrian is going to focus a little bit more on the hardware and the ROI of that hardware, what's going to have the biggest bang for your buck. And then my main focus is the modeling methodology side of things. What things can we do to SolidWorks and the settings inside of SolidWorks and the different options of SolidWorks to get the most efficient model possible. We'll finish it up with a finale, take time for questions at the end of everything.
So what we were talking about this morning, or what Bertrand brought up this morning, is that theme, design without limitation. Okay, and that's what we're striving for, as I mentioned before. And to do that, our small portion of that is to give a better understanding of what factors are involved in your SolidWorks environment that are affecting your performance, and which ones have the most significant effect on your performance, so you can make the right decisions going forward in both hardware purchases as well as modeling techniques and methodologies that you employ. Okay? So, the end goal being what I said. Let's make the computer wait on us. All right?
All right, the why of the presentation. We always wish we could have better performance. That's something that everybody's always looking for. How can we get through the day faster? We've always, heard back from our customers that the hardware and the operating system is IT's problem. And actually, it's really your problem. It's your job as the engineers to go forth and convey to the IT and upper management exactly what you need and why you need it. And that's what we're working on here. Also, we're never taught proper modeling methodology. Any of the classes that you've taken, for the most part, they're going to tell you what the tools are and how to use them. They don't tell you how to use all those tools together and what becomes the most effective way of creating your models at the end of the day. Lastly, how do I maximize my ROI? Where is that break-even point? Where is the point that I'm spending too much money on my hardware? That's what we're also looking for here with this presentation.
All right. We're going to use a couple of workstations to base our testing on. Box Technologies has been kind enough to loan us a Box 4920 Extreme workstation. Gives us a broad range of possibilities in our test, changing everything from processor speed, number of cores, and then a litany of hard drives that we get to work with to determine which ones are going to be the most effective in a performance standpoint, but also what we're trying to do in these tests is figure out where we went too far. Where did we buy too much hardware? There is a way to go over the edge, and we're going to try to avoid that. So a couple of key highlights here. we're working with i7 chips with 6 cores. This Revo drive here is a pretty slick hard drive. It plugs directly into PCI Express slot of your computer, and it's just lightning fast. It comes from a company called OCZ, and it's really a sweet piece of hardware. Also, NVIDIA loaned us about 5 graphics cards so we could work and figure out what the chances are, or what the different differences are with the different cards as we go up through the product line. We even got ourselves a GeForce 650 Ti, which is unsupported gaming card, because everyone asked us about it. So let's see what happens when we actually use one of those and what the results are. What does happen when you go unsupported? All right?
All right, so the model itself, if anybody's seen our presentations before, the model that we've used for our testing, we've never been able to show to you. It's always been a combination of different customers' models, things that we've put together over time. We actually found kind of the perfect model this last time around. A company or customer of ours, Racine Railroad Products, they gave us the model that you see over here on this screen, and it is for the rail industry. And what this thing does is it actually puts in the clips that you see there into metal and wood ties. So, and this thing, it's a beast. I mean, when you look at the assembly statistics there, there's 10,500 components in there. You can see there's several unique, over a couple thousand unique part documents, sub-assemblies. It goes several levels deep. There's a lot of top-level mates. So this is really the ideal file set for us. Gives us a whole different bunch of different aspects to look at, different things to test and try out. Overall, when we look at this, the folder size for this guy was close to 2 gigabytes and almost 4,900 files in the file set that we got from the customer. So it's a pretty significant set of data that we're looking at here.
So the test we did, we built a benchmark that was not only going to, we don't want to just rotate through the model a bunch of times, do a bunch of rebuilds and say this is what your performance is. We went through actual functions and processes that you go through in your day-to-day life. We not only open the models and spin them around, but we do modeling changes to the models as well. We make changes to the drawing of this big assembly as well, so that we can get more of an idea of what's really happening to your performance as you see it day to day. Okay? So those are the things that we are changing, or the things that we are going through when we run our benchmark. It's a completely automated benchmark as well, so it takes that human element out of it as well. And you'll see when you see the runtime, we weren't going to push the button that many times. It takes a long time for this thing to run through its paces. Well, at least in the beginning it does. Things that we're trying to compare, or the ways we're trying to compare things, we have a benchmark that's kind of the typical machine that we see from a customer. It's a low-end machine that we start with, and we keep changing things one thing at a time so that we can measure the effect of that one thing. Now, we've always done it one thing at a time and then backed up to the baseline and changed one more thing just to see what would happen, always measuring that one thing. This year, with hardware, we're doing a cumulative change. So we're going to change RAM, and then we're going to stick to what we find there and those results. We're going to use those results, and then we're going to change something else. And we're going to continually build up to a machine that we think is a more practical machine for use, as well as what we'll call an optimal machine. All right?
Or overkill.
Or overkill, optimal overkill, whichever way you want to look at it. Now, also, we'll test methodology, but that will be changing one thing at a time. They will not be cumulative tests there. And we'll see what these changes can do to our performance. Now, remember, one important thing about these tests is this is an environment that we set up. It's a model that we've controlled. It is very specific to, well, not our needs, but our environment and our world right now. Your benefits that you see from these changes, if you make them in your world, are going to be different. They'll be similar, but maybe on a different scale. If you do smaller assemblies, you're going to see less of an impact, potentially. All right? If you do larger assemblies, greater impact. So And there are other factors involved as well that you got to take into account. Things that weren't tested. RAID. We've done this for 3 years previous to this. We know the results. RAID doesn't help us that much. And it's a pain to set it up. It's a pain to pull it apart. I didn't want to do it again. 2012 to 2013, I just lost the results, and he won't let me hear the end of it.
It's one of my
Okay, I
tests.
tested it. I don't remember where I left the results. They're gone. Live with it. Okay, 32 bits dead. We're not even going to worry about it, so we just moved on.
Anybody using 32-bit still?
On my job, I cannot get them to tell us to switch. They
All right.
will not switch.
Well, we'll give you a reason today.
Yeah, show them this slide.
Yeah.
At least give them our attitude. You know, maybe that'll help. All right. Antivirus and network storage. Well, I ran out of time. I couldn't do any more. All right. And verification on rebuild. We used to test this one every year, but no one's actually screwing this up anymore. Okay. If you have verification on rebuild, or if you don't even know, just go to your system options and check and see if it's activated. If it is activated, it's costing you big time. Yes, sir.
You were running your test, you run other applications other than the SolidWorks itself.
No, I did not run. That's a very good question. We ran no other applications but SolidWorks, and we went so far as to dig into the operating system and pull out anything that was going to run as a scheduled task that might eat any of our resources. The reason being is because, well, let's just say if it's doing some kind of a check for updates, or maybe a disk defragmentation is a better example. It's going to do it at its random schedule, or whatever it is, in the middle of one of my tests, and then that test result is going to be different than the rest of them. So I'm going to have an erroneous example there, an erroneous result, and I'm not going to know why. So we stripped it out to nothing but SolidWorks, so that is all we are comparing, at least as close as we could figure out. And we got some really good results. And swap. Swap is something we needed with 32-bit. With 64-bit, you need RAM. You don't want to use swap space. That means you didn't buy enough RAM and you're hurting in your performance because of it. So we don't test it anymore because we don't want you to use it anymore, or at least not need to use it.
All right, so the benchmark itself. The test that we've run, or the benchmark that we've run in years past, it used to be a macro that we had written. This time around, we had Bob Hansen. He's one of our CATI and inflow techs. We had him help us out in running an API for creating this. We get overall better control of our tests, easier turnaround between those tests. It allowed for a lot more flexibility in what we were able to get results for this time around. It was much more stable than our macro, and the results were cleaner overall. We were a lot happier with the way everything turned out. It just seemed to be clean and consistent across the board. So that's what we ended up with for our benchmark. The baseline model that we started off with, like Adrian said, we started off with a baseline, or what we consider to be a typical model. It was running SolidWorks 2013 SP0. That's what we had available when we started all of our testing. And you got to remember, we've been testing for close to 6 months now at this point in time, getting everything set up and built and running the right way. Win7 64-bit. Our SolidWorks options to default, with large assembly mode being the exception. We made sure that one stayed off. 8 gig of RAM, our OS and visual settings at the default, 2 cores on our machine, and a 7200 RPM hard drive. For SolidWorks side of things, internally, we left the image quality set to what we would consider to be the optimal setting. It's right around 25%. We have a high level of detail in the models and a large number of top-level mates also. And we've always been loading the assembly fully resolved at all points in time. Yes?
Large number of top-level mates. There were 139 over there?
No. We'll show you a little bit later on. There's actually closer to 1,300, and I'll show you why there's 1,300 in there. So there is a reason for that. Yes, you're right.
Oh, back up one. You didn't show them the runtime.
Oh. Our runtime overall, 4 hours, 43 minutes, and 44 seconds is our baseline runtime. And what you see here, our scoreboard, Adrian's flipped over here for us. So we got our typical machine in there. This is the layout that we just talked about. We're running a Quadro 600 for the graphics card. I don't think that was in the list. Baseline cost, $2,600. We have our baseline runtime there. You'll see the typical and optimal machines. Most of the selections for that right now are grayed out because as we talk about these different items, we're going to find what is the right setup for each of those items. And you're going to see the cost of the machine change, the delta change between those machines, time, delta, and percentage of that. And each one of these is a comparison to the other one. Typical, our practical machine is compared to our typical, and our optimal machine is compared to the practical. So each one is a step up.
All right. So like we said, we've been doing this for a long time, a few years now, doing this extensive testing. And what we found is you got to start everything with RAM. When you're dealing with larger data sets, larger assemblies, RAM is the linchpin to everything. All right? So that's what we did. We ran these tests, realizing that without enough RAM, what's going to happen is your hard drive becomes even hypercritical because now it's being used for swap space. And while it's doing that with the swap, it's not operating SolidWorks efficiently. It's not operating your operating system efficiently. It's slowing everything down, no matter what it is. So not having enough RAM makes everything just much more difficult. Also, in tests we ran last year, we could drop the amount of RAM, drive up the amount of swap space to compensate, and make the machine so unstable it couldn't complete our benchmark. Okay? You don't want to use swap if you can avoid it. And this is what we came up with, at least the basic chart. And what we can see, if we look closely, and that's why we made this chart as big as it is, there is a point right in here where we get no more performance gain. Every assembly, every part and assembly that you have has a threshold. This is how much RAM it's going to need. Once you reach that threshold, you're done. Everything else is overkill. It may run a little bit faster, but not enough to make a significant difference. All right? And this is what we found. Now, the gray numbers, the bolded numbers, are what we considered the typical. You can see over on the other screen the typical. And that's what happens when we drop off just 2 gig and we start driving that hard drive even harder. Remember, our typical hard drive is a 7,200 RPM drive. That thing is just not fast. And we're suffering for it here. And when you start going 161% slower, you notice it. It's a big, big deal. Now, when we got to 14 and 16 gig, you can see 58% improvement, almost 59% with 16 gig. Actually, our sweet spot is probably somewhere around 14 gig, but who can buy 14 gig of RAM, right? You got to buy 16. Right? There's no, I don't think you can. So, but then the real trick here is going all the way to 32, you get another, what's the math? 0.6. Sometimes I struggle. All right? So 0.6, another 0.6. Do you think that's worth it? For some people, it might be. For some operations, it might be. But for us and what we're testing today, it's not. And for most people out there, it's not. Because there aren't a lot of people doing 11,000 piece assemblies. Go ahead.
All right.
So what we have is our practical machine with 16 gig. Optimal was a little bit faster, but not much, meaning that with our practical machine for an extra $200, we dropped 59% out of our test time. That's huge. And if you want to spend another $200, you can get that last 1.5% if you think it's worth it. All right? That's what we mean by optimal. What we would probably call overkill at this point. All right?
In our environment.
In our environment, in our model.
Exactly. All right, so the next thing that we take a look at is processors. How many cores can SolidWorks use? If you guys have been using SolidWorks for a while, most everybody should know that SolidWorks uses, for most of its operations, it uses 2 cores. The operating system can use an additional 2 cores, and other applications are going to add to that load as you go on. Simulation and rendering, they can take advantage of many cores, and we have a little kind of sidebar that we're going to get into after we talk about just the initial set of cores here for exactly the simulation and rendering purposes. So what we look at here as far as processors go, 2 cores, that's where our typical machine was at. Like Adrian said, you take that step back with RAM and you saw how much of an increase there was there. You go back to 1 core. Now SolidWorks, your operating system, everything's running on that 1 core, almost 300% slower at that point in time. So that's just eating hours of your day. If you go up to 3 cores, we gain a little bit, we get up to 13.8% faster. 4 cores, 6 cores, we're kind of starting to flatten out at that point in time. So for what we're doing here, in just SolidWorks processes alone, not simulation, not rendering, our typical there was the 4 core, and when we switch over here to our practical and our optimal machines, we look at 4 cores is going to be our practical, 6 cores is going to be our optimal. So at that point in time, for an additional $745, you're gaining almost 65% worth of performance there. You step that up a little bit more, and we're sitting at 0.5% faster. So the choice is up to you as far as which way you go with that. But look at the 4 cores, I think, is a good starting point.
Now, something to remember about the scoreboard that you see, a couple of things to remember. One is, this is cumulative. When you add this much RAM and add the more cores, that's the total delta and your total change in performance. Oh, I'm sorry, I knew that was coming. And then these deltas are off of this. So your optimal is compared to your practical is compared to your typical. All right? Keep that in mind. Also, all these numbers are ballpark numbers. It's going to depend on your vendor. It's going to depend on what kind of discounts you get. It's going to depend on the quality of the hardware that you get. All of that's involved. Just remember, we're talking about ballparks, right?
All right. So like I said, we're going to take a little bit of a side shoot here for the processors and talk about the workstation that we used for simulation and photo rendering. This is Corona, is the name that we gave this machine. It was another box machine that they lent to us, a Render Pro. This one here, it's running dual Xeon processors, dual 8-core processors, or 8 cores each, 32 gigabytes of DDR RAM, 750 gigabyte hard drive, and an NVIDIA Quadro 600. So this machine that we have set up here is great for exactly what we're working on here. Now, the Xeon processors that we use for this machine, the reason that we went with Xeon versus the i7 that we have in the other machine is it's Intel's only processor to support multiple processors in a single workstation. It supports a greater system memory bandwidth, also larger memory capacity, and ECC RAM, which is preferable for our larger memory configurations that we have here. 32 gig of RAM, it's a lot of RAM for a machine. So, and what we got here, sorry, stepping on you.
Well, what we want to talk about is where we need more cores, and that's specifically why we got a separate box for this purpose, because we wanted to explore as many as 16 cores and what that's going to impact. Now, we know with SolidWorks it's not going to do much for us, but many of you out there have a lot more going on than just SolidWorks, right? Now, just having, and we've proven this in the past as well, just having Outlook running, an ERP system, some kind of purchasing system, any other thing going on in your computer for your company related, weather bug, for Christ's sakes, don't do it. But, I mean, all these other little things take up resources and bandwidth, and the more of that stuff you do, the more cores you may be able to take advantage of effectively. Okay, so that's one reason. Simultaneous apps is a good reason to go to more than 4 cores if you have enough of it happening. Simulation and photo render, though, give us an opportunity to take advantage of a lot more cores and get a lot more benefit out of it. And that's what we want to discuss right now. Simulation particularly. Now, we have hyper-threading as well, splitting these cores up and simulating more cores than we actually have. Now, with simulation, that actually didn't help us out much. In fact, If you look at right in here in our flow simulation that we did, when we get into the higher numbers of cores, hyperthreading actually hurt us significantly, okay? And just so you know, when things like this happen that we're so far off the norm, we tested twice, 3 times, just to make sure we weren't getting anomalies. That's kind of frightening. With simulation, hyperthreading is just not helping us out. We're not going to use it. So it does help if you got 1 or 2 cores, but realistically, how many people have that anymore? So that's not going to do much for us. And no improvement beyond that. Now for flow, we did a pretty substantial simulation. It took quite a long time to get through it. And from 4 to 6 cores, when we ran that test, we get 17% faster just going to 6 cores. Now, think about it. The i7 that we're using in our other workstation is a 6-core processor. It would not take much, monetarily, to go from 4 to 6 cores there. Now, if we want to go from 4 to 8 cores, now we're probably talking Xeon processors. So we're switching to that platform, and we can get that in one Xeon processor, 8 cores, and we can get that 20% faster than our baseline. Substantial amounts, and if you do a lot of simulation, a lot of flow simulation, that can make a big difference. And then from 4 to 16 cores gives you even another 9% on top of that. That's not bad. All right? It depends on what you're using the software for, what you're using the machine for, as to whether that makes sense for you or not. All right? Thanks. We did static simulations as well because it's all different. The mathematics is different. The way they use the processors is different. Everything's different. And we saw some different results as well, somewhat less impressive than the flow results. But again, if that's all this machine does, you want it doing it as fast as possible. And it could be very well worth it. All right? So, photo rendering?
All right, so talk a little bit about photo rendering here. While this is playing, I think Adrian, there you go. He's a little slow on the uptake today with his clicks. So for photo rendering, what we found out with photo rendering, if anybody's done it before, the more cores, the better. If you've done any photo rendering, you see the little pixels on the screen as you're doing your rendering. That's signifying the number of cores you have there. If you got 4 cores, you see 4 little boxes rendering at each time. So the more cores, the better. Hyperthreading definitely helps in this situation, as much as 16.8%. And what we want to look at here, though, is, with the curve that we have here, it doesn't look like there's much of a gain when we go past that 4 core there. So if we go ahead and zoom in on this and look at that range of 4 to 16 cores, you can see that there is actually a significant amount of improvement there. Going from 4 to 6 cores is going to gain you 17%. If you go up to 8 cores, so getting that Xeon processor like Adrian was saying before, one processor alone is going to get you 51% faster on your renderings. Go ahead and double that up and get up to the 16 cores. You're now running 74% faster on your photo rendering. So it's something that if that's what you do day in and day out, it is going to save you a huge amount of time. It's going to get more renderings out the door, make your job that much easier, much more efficient.
Now this machine that we were using, this Render Pro, is built for this. They call it their stripped down, souped up version because it's actually a box about this big on the front profile. It's fairly long. They got enough fans in it to choke a horse to pump all that air through to cool it down. But it can pack in RAM and processor, but it doesn't worry about the other fluff. You've got no expansion room. You've got no, because it's not what it's built for. It's built to use those cores to their maximum efficiency. So think about that sort of thing as well when you're going forward and you're looking for machines to serve purposes. Find a machine that's built for that purpose can help you out. Everything's different. Everyone's got different needs. So it's good to... Did that thing stop on its own?
Or you clicked one too many times.
All right. We're good.
All right.
You didn't... Did you do that? We're done?
Yeah.
Processor speed? All right. Now, SolidWorks is limited on the number of cores it can use. We know that. So we're back to our world of just SolidWorks. We've passed by simulation and photo rendering for now. So if you've only got 2 cores and that's all you can take advantage of, you want those cores as fast as possible, right? That's what you need. You need to see them move. We're constantly cranking and getting through the calculations as quickly as possible. So I think I just hit it. Can you hit yours?
Yep.
All right. So when we started changing the speed on our processors, we started getting some pretty cool results. I mean, this is a machine that allows us to overclock our processor. And it helps us in this testing phase. Yes, sir.
What were you using for
Cooling?
water cooling?
I'm sorry?
What were you using for cooling? If you're overclocking the CPU, you have a heat problem.
Yeah, I believe it's, Shoaib, is it liquid cooled? Yeah, it's liquid cooled. Yes. Now, as we go through, and we kept bumping up the processor, bumping it up, going up to 3.78, I mean, another 8.2, go up another, 0.26 or 3.6. We're at 11.5% faster. We just keep getting faster and faster. There's not a limit in this test. So what we end up with, you went 1, 2, is the practical. This is the only point in the presentation where the practical and the optimal are actually the same thing. And it makes sense for an extra couple of $100 to get up to that level based on the differences that we've shown. That delta's wrong. It's supposed to be the cumulative delta.
Yeah, it is.
Okay. So, we're 70% faster. But on the optimal, look at that. We're still only 2.5% faster. So, moving on.
All right, so the next thing to look at is hard drive speed. How important could it be? Like Adrian said before, when RAM is in short supply, hard drive speed is definitely critical at that point in time because all of our swap is moving over to that hard drive. RAID, like Adrian said once again before, we tested it before, 3 years running. We found little benefit with it, so we skipped over it for this, for our SolidWorks applications. It may work out well for some other applications you're running, but not for what we did here. We did not test multiple drives for different roles. We've done this in the past, but now that we don't need a separate drive for swap because we aren't worried about it, we didn't test those multiple drives for different roles. So we just stuck with one hard drive at all points in time. And what we saw, our baseline machine, that was run that 7,200 RPM drive. As we go through the 10,000 and the 15,000 RPM drives, we get a little bit of speed. But where we really start to see the improvement in performance is when we jump up to the Intel SSD drive. It cut down our testing time by 13.1%. And if we went to that Revo, that hard drive card that Adrian was talking about, it cut us down another 1.2%. So obviously that's where our practical and our optimal machines are going to be set up at is Adrian.
Josh. You have to see me hit the button or what?
Exactly.
Just watch the
Exactly. All right. So our SSD and our Revo, those are our typical and our practical and our optimals at that point in time. And you can see that we got the right delta on there now. For just a little over $1,200 now, we're saving 72.6%. And if we go to that optimal, we're over $3,000 more than our practical machine, and we're only gaining 2.8% above that original 72.6%. So,
yes, sir.
Yes.
This test, the SSD is going to be critical when you in the I/O stuff, right?
Correct.
So, which part of it of your benchmark is like open file, closed file? Give a percentage of the improvement for SSD. I don't know how much I/O is involved.
That's a good point, and that's one of the vagaries of the process that we have because the benchmark, because we have a whole different assembly. What we've done is we've copied the data set from one location to another on the hard drive just to start out. We've launched the software, which takes some I/O as well, just to get it up into RAM. Then we've opened that entire data set, and then we started working with it. We're all in RAM. Okay.
Opening other part components, closing them, opening up drawings, changing them, closing them. So we've done, hopefully what we can represent is a fairly, significant number of opens and closes that would be what you would do in the course of a typical day. It's not just one open and close. It's, it's several.
It is several. So I know exactly where you come from. It's hard to know what impact it's going to have for you because you might be opening smaller data sets more often or larger data sets less often. It gets difficult. But there will be an impact. I just can't tell you exactly how much. So now we want to talk about graphics cards and what your needs might be. This is a very difficult area to work in because there are so many possibilities and so many just facets in your environment that affect your graphics performance. Okay? So this is what we tested. All right? Was that supposed to go over? I don't think so.
No.
Functions that we tested, display states, whether your wireframe or hidden lines removed, hidden lines shown, shaded with edges, shaded, all that. Shadows, real view graphics, your image quality. How many people have set their image quality properly? All right. We'll talk about that a little bit as well. Transparency. What does transparency do in a model? It actually makes a very big impact in models depending on how it's used. And lightweight and large assembly mode. What does that do for us? As well as level of detail anti-aliasing we looked at as well. But we tested 3 different models. We tested a very large assembly, the one we tested for everything else. We tested a small assembly, probably 200 components? Something like that. And we tested a single part. We ran them all through the same macro that spun them around like for, 9 to 10 minutes. All right? And just kept spinning them like all heck. All right? Just to see what we could get in the performance. And then we tested all 5 of those cards. The first 4 are supported, professional level cards, and then the last one's the gaming card. Yes, sir.
All these functions you tested were did it once, all of them? Or you just played
One at a time.
one at a time?
Yes, we tested each of these things one at a time and measured the results. In a single session. Not in a single session of SolidWorks. No, we switched sessions to SolidWorks. Yes, sir. No SLI. We did not. I don't believe SLI is going to give us even a little bit of benefit, but I'm not 100% sure of that. All right. So, Josh.
Our graphics card functionality. So what we ended up with for display states, shaded was where our baseline was. Shaded with edges, we were 25% slower. You go hidden lines removed, once again even slower. The real killer, hidden lines visible, it was 139% slower for our test here. Wireframe, 100% slower. So the sweet spot as far as graphics cards, you want to be running just a shaded model would be where you want to be. Shaded with edges isn't costing you that much more.
Now, NVIDIA's made a lot of adjustments between 2012 and 2013 where, like shaded with edges, happens a lot faster in 2013 than it did in 12, but we are just in the 2013 world. So we're not measuring that improvement that they've made. So everyone's
Yes, sir.
aware.
Yeah.
Yeah, staying shaded. We did not try AMD drivers or cards at all.
We weren't really trying to put one card against another. We were trying more just to test kind of a whole product family. So
Yeah.
all right, so image quality. What happened when we adjusted image quality? Like Adrian said, it's something we're going to talk about even more in the modeling methodology section. But image quality plays a big impact on everything that we do, even down to our graphics performance here. When we got that image quality slider set at 20%, that was kind of our typical, that's where our baseline was at. But you see, as we bump that up, we hit the 90% range. We're 115% slower at that point in time. And you can see how that curve takes that dramatic jump up. Basically, if you're in that red zone, that is death as far as everything is concerned. It will increase your file size. It increases everything. So like I say, we're going to talk about that a little bit more. We couldn't even run it at 100%. We ran the thing all the way up to 100%, and it took so long for the model to actually, rebuild and try and resave it that we actually crashed the machine when we were doing that. So that's why we stopped at 90%.
All right. Other things that we compared, real view graphics on and off, you can see, you could expect you're going to get a performance decrease there. And transparency, it was actually surprising to me. It can be up to 50% slower if you've got significant transparency in your model. For us, it was 41%. You expect some degradation. I didn't expect quite that much. But for lightweight and large assembly mode, what we're going to find in this, like for everything in SolidWorks, graphics is the same way. If you lighten up the models, if you pull out that extra information, all that extra data, the parametrics that it's calculating in the background all the time, you're going to be a lot faster. Okay? Now, there's flexibility that you lose there in some way and shape and form, but not a lot when you're talking about lightweight modeling. So when you're doing large assemblies, we greatly recommend that you use that functionality.
All right. So for our graphics card comparison, our supported cards, large assemblies, what we found, anything from the 600 all the way up to the K5000. If you were working on a large assembly, we only saw about 2% gain in performance across the board for all those cards. For smaller assemblies, that's where we really start to see the performance improvement. That 200, 300 component assembly, you can see going from the 600 to the 2000, we gained almost 35% at that point in time. Going from the 2 to the 4, a little bit more, and the 4 to the 5, just a little bit with that. So, and then the GeForce card, it ran, but once again, you get no real view graphics with it. It's unstable. It was overall 10% slower than that Quadro 600 card that we ran. No full scene anti-aliasing, no stereo or 3D capability. And bottom line, it's unsupported. So while it may run in, 2013 Service Pack 0, the next Service Pack you come out with, it may not run.
I would have expected the large assembly to get bigger.
We did too. Basically, what I believe is going on there is there's a lot going on in SolidWorks in the background, especially with large assemblies. There's a lot of massive calculation that's happening, and I think that's becoming the great equalizer. Your bottleneck is becoming SolidWorks getting the information out to the card. I don't know if I'd say that, but I think it's just the way SolidWorks is handling the data. It's just not they're not taking advantage of the power that the cards have. There's a lot of GPU and RAM on those cards that just aren't being used, especially in these large assembly situations. I would have expected the same thing you did, a much greater performance change. Now, what we did find is that in the small assemblies and the parts, it does get faster and faster and faster as we would expect. As you go up the line, it is getting faster in a diminishing kind of rate, which I would also expect. The problem, though, that we're seeing is they're getting so fast up here, I'm not sure you can see it with your eye. They're just blasting it out. So the large assembly is over 10,000 components. The small assembly is somewhere between 200 and 300.
So, and that, to me, the 200 to 300 range is what you're going to see typically for most users on a day-to-day basis. You aren't going to have that high level of assembly all the time. But,
and that's part of the reason that we stop here and we talk about this for a little bit is because with these numbers, the way they look right now, there is a case that could be made for making the 4000 the practical card to buy. We chose the 2000, okay? We chose the 2000 as the practical in this case. And the fact that it reacts differently for different size assemblies is just more to study at a later date as we go forward with our testing and our research. But the bottom line there, the way it feels, is something I want to make sure everybody understands as well, because performance in a graphics card is not only measured in how fast it can get from point A to point B, which is generally what we're testing with the way we run our test runs. You can go from point A to point B, and cards are going to get there. But how many frames will it paint on its way? How smooth will it look to your eye as it's going across? And how important is that to you? You know, level of detail is an option you can set in system options, right? And you can change that so that you'll get a smoother drag across your screen. I can't test that right now, how you move it across with the mouse, because I can't hold down that left mouse button while I move the model in a programmed macro situation. So the way it feels is very important to most users. That's where you feel the performance of a graphics card. And we feel that you're going to get the best bang for your buck in the 2000, the Quadro 2000. Right? Yes, sir.
When you ran those tests, was like a real U1, was it shaded with edges or not shaded?
Very good question. What state was it in when we ran it? What we did was we ran it in each individual state, right? And that's a very good question. It's important to know this. We ran it in each individual state, including the baseline. We did a cumulative average of all of them to get that number, okay? So, and we ran it once with everything turned on. And we did not include that in these numbers. The reason is because the cumulative average of everything turned on was giving performance degradation in the 600 to 700% range. And that was throwing things off quite a bit and giving a kind of a false impression, I felt. So we cumulative average of all those things individually to determine what our numbers are here. Did that make sense?
Yeah, but when we had those 600, 700% differences, did you see variation between those cards? I mean, was it always, was it 700% slower on all cards?
Oh, I see what you're saying. Was the 7, it followed pretty much the same curve you see here, pretty much. I think there was a bigger tail-off in the tie-in than I would have expected. But it was similar.
And we've done testing on video cards for several years. This is the best test results that we've gotten so far. And so all I can say is, come back next year and we're going to be doing more testing. We're going to be doing more work with NVIDIA and trying to, find out what is the best way to test these things. It could be some of the way that we're testing it. It could be, it could be several different factors. So we're continuing to learn as we go with all of this. So. And there's also other reasons that you want to run these cards. There are several other applications, third-party applications out there that do take advantage of the GPUs, and there is a case for utilizing it at that point in time. So,
all right.
Did you have a question in the back?
Now, he asked if we had stretched SolidWorks across 2 monitors and tested it that way. I thought about it, but I'm sorry? Going across 2 monitors? I'm not sure anything likes that too much. Stretching across 2 monitors, using SolidWorks in dual monitors is one thing, but stretching across both of them, you're going to see some instability. We've seen it in many cases and in many different cards. So I wouldn't switch cards in hopes of fixing it. All right. I'm next. Now, we made the change, the practical machine. We're filled out our scoreboard at this point. And we see that just in hardware, we haven't changed methodology at all. Almost 73% increase for another $1,500. Ballpark numbers, remember. And if you want to spend the extra $3,300, $3,400, you can get an additional 2.8%. It is possible to overbuy hardware, okay? The key is to know what your needs really are and know what the limitations of the hardware are before you go in and make the purchase, all right? I mean, those are some pretty astounding numbers when you think about it. And I've got a few customers that buy these big gargantuan machines because they have a large assembly. And I can guarantee they're not getting their money's worth out of it. But it does look nice and shiny on the shelf, right?
And plus, I'd rather, show this to my boss and have him give me the difference in cost there as a bonus or something like that for saving him some money. So, even half of that would be
I'm his boss and I ain't going to do it. So
it's worth a try, Adrian. Come on.
You can try. But it is. I've also seen IT departments pop out high-end, what we would call optimal hardware, and get it down to an engineer as fast as they can just to shut him up. Doesn't generally work. What we're going to show next, though, in methodology,
is all the things that we can do. The next section here is really just to do methodology testing as far as what modeling methodology you see that's going to give us the best improvement. Each of the tests in this section, we are doing just a single change, and we're comparing those against our typical and our baseline machine. We all agree that the optimal, like we say, it's a little bit of overkill for our scenario, so we're just going to run these tests against the two different scenarios. These tests, they're in no real particular order at this point in time. We just did each one of them. We tested out a lot of different things that people have asked us about over the years, all the different settings that you have, or a lot of the different settings inside of SolidWorks that we feel have an improvement or a difference in performance. So, first thing that we look at, files stored in an older version. As crazy as it sounds, it is something that is a factor here. Does the age of the files matter? What we did is we took a bunch of files, our original data set, that was not converted all the way up to 2013. Some files were, some files weren't. Some files I think even were back in 2010. So it was all over the place. As few as one file we've seen not saved in the latest version can increase open, save, and rebuild times. There's something else that, so it's another thing that SolidWorks has to look at and figure out exactly what's going on with those files every time it does those operations. So what we end up with here, we only tested it against the practical machine. It actually didn't even run on our typical machine. But leaving files in an old version, not saving them up to the current version, cost us a little bit over 14% against our benchmark. So it's a significant amount of time. Make sure you get your IT department, take the read-write access off of those files that are stored in the libraries, update them to the latest version, and you're going to save a little bit of time.
Comment on this? Just want to tell you that I was talking to R&D people, and they explained that whenever you open an older version file, it has to do with verification or rebuild for this file.
All right.
Actually, what we're doing is turning on verification or rebuild for this operation.
That's cool. Okay, so what this gentleman's telling us is that every time you open up an older file version with talking with development, SolidWorks is actually doing a verification and rebuild on that part that's opening up from that older version. So there you go. Adrian told you before that verification and rebuild will double up your rebuild times, and that just proves it right there. So that gives you a little bit more background, a little bit more incentive to save up to the latest version. So thank you. I appreciate that. So system options. How do we choose the right option? What we did, we went through all the different system options there. You can see all of them across the screen there. We changed 18 different settings inside of the system options. We didn't include lightweight or large assembly mode. There's more to come with those tests a little bit later on. Most of these settings are that we changed are items that are visually appealing. Things like rotations and image quality, things like that, or not image quality, but little things inside of there. View transitions are all things that we changed. There's a complete list of these settings on the slides at the end of the presentation. When you go and download this later on, you'll see all those different items. All right, so what we end up with our SolidWorks options set to optimal, we gained 16% on our typical machine and another 0.2% faster on our practical machine. You can see, once again, hardware will buy you out of some scenarios. This is one case where, like I said, a lot of these are visual things, so having that additional RAM, it really helped us out a lot in that case there. All right.
All right, this is one of my favorite ones, and if anyone's seen me present before, you've probably heard this. Never, ever let Microsoft make a decision for you. They will not do you well, I can guarantee to you. You got the lanyards there. I'm sorry. But, can you hit the button? If you go to Properties on your computer, to Advanced System Settings, and go to Performance, all right, what you're going to see is Visual Effects in the first tab there. Now you'll notice that just about everything is checked, and you have some options here. First, let Windows choose what's best for my computer. Microsoft can be evil. If you adjust for best appearance, look what it does. Now they're all checked. You went from one thing being not checked to everything being checked, and no difference whatsoever. But if you want best performance, so what they have told you is that Microsoft believes that what's best for your computer is that their operating system looks as pretty as possible, but your performance goes through the dumper. Now, I thought at one time that maybe if you were on a server, this would be different. It would be set different because no one's looking at a server anyway. What's best for that computer would be performance. It's not. They've got that one set the same way. There is no need for 4 buttons here. Not at all. You only need 2 or 3. So, wait. But what it does, why is that SolidWorks options? That says SolidWorks options, but that's OS options. How could we go through this many dry runs and not catch that?
I don't know. You put that one in there, not me.
It's your fault. So, let's pretend that this says OS options, all right? But we gained 16.6%, almost 17% in our typical test, and on our practical machine, we still gained almost 4%. It's worth doing. It's free. It takes you one button click, and you got 14% or 4% extra performance. Why not do it? You got to love that. All right, you're up.
All right, so the next thing, like we said before, we talked a little bit about image quality before and what it can do for you. Is too much a bad thing? Most definitely. Whenever I get an assembly sent to me for performance problems, this is the first setting that I look at every last time. I always start at the top level assembly and look at that and see where it's set at. Set around 25% is where we say the sweet spot is. You can see the image that you got there, it still looks like a circle. You go below that 25%, now it starts to turn in kind of a polygon or octagon at that point in time. But that 25% for most people is perfectly fine. We showed evidence of this in the video card testing. This is a per document setting that you need to remember that. And one other item that to note here, changing at the top level assembly also allows parts to be changed. So if you look here, went one too far. Back there. If we look here, apply to all reference part documents, that's the checkbox that you want to do. Open up your top level assembly, open up your top level drawing, check that. When you save it, it's going to go down to all the individual part files. It does not change at the subassembly level though. So that is the one thing to note with that. So, and what we see with that, as far as our settings go, if we set our image quality too high, we get up near that red zone, we're on our typical machine, we're almost 300% slower at that point in time. Once again, that RAM plays a critical factor because you look at our practical machine, we're only 15% slower. So you can buy your way out of some of it, but there's still some performance to be gained by turning that slider down and leaving it at what we consider to be a reasonable level. So, not to mention also, this does increase file size the higher up this goes.
applies to all reference documents. Yeah, that when you check that and you hit it, it's gonna set that down through your model, through your assembly tree.
It doesn't change the sub-assemblies, no. That's the one thing I found when I was looking at it in 2013. Granted, that was source pack 0, so that might have changed a little bit, but the last time I checked, it still wasn't going down to all the sub-assemblies. So,
Real view graphics and shadows. Again, it's stuff that makes the model more appealing to the eye. Yes, sir.
About that optimized display option.
higher quality but slower, we leave it off. As soon as it says higher quality but slower, if it says it's going to make it slower, I'm going to leave it turned off at that point in time, yeah. No, it's nothing that I've tested, no. As soon as I see the word slower, I'm like, if SolidWorks options are telling you it's going to make it slower, why would anybody turn it on at that point in time? So, just as a general thing.
So real view graphics and shadows. Again, it makes things more appealing to the eye. You can show your boss the assembly and make it a lot more manageable for him to understand what's going on in a lot of cases. You can show it in a real photorealistic manner while you're modeling, and all of that's great. But it is going to cost you, as you can imagine. You're going to make it a little prettier, but it is going to cost you in some performance. It takes a large amount of system resources, especially in RAM and processor, to do that. But we have a fix for you. For real view and shadows, we have a macro that's available. You can contact us at a later time, and we can talk to you about it. A macro that'll go through and turn off real view and shadows, as well as set that image quality down to a proper point. And you can run that macro against a file set and just take care of all of it at once. We've had a few customers that have run real view graphics or even image quality and had it turned on for everybody, and now they've got this huge database of files that are just set wrong, and you don't want to go through that manually, so we help with that. Now, another thing to remember about that, though, is especially with image quality, to back up a step, with image quality, that is a document setting, and it starts at your templates. So if you've been using SolidWorks for a long time and your templates are built off the old default templates that SolidWorks gave you from years ago, their image quality is set way too high. And if you didn't go in there and set it back, you've been working with too high an image quality for a long time. So you might have some problems in there. So just check it. Check your templates as well as your current parts to make sure you're okay going forward. Now, whoops. Real view and shadows. 20% faster on our typical machine and 2.7% faster on the practical machine. So it just depends. Is it worth it to you to have that extra visualization available for 2.7 or 20%, depending on where you fall in that line of machine? All right?
All right, so part and assembly details. If it came from the internet, it must be okay, right? All right, everybody knows that's incorrect. For our assembly here, we cleaned up just the cab assembly. So you saw how big that thing was. We only cleaned up one portion of this, basically 1/4 of the assembly. We cleaned up the cab, its related parts and assemblies. You can see the stats on the cab there. We remove part details like extruded text. You see our display panel there. How many people go through and make that? Cut every last letter into it. If you zoom in on that, you will see all the little faces that are created on the inside of those letters. Create configurations of imported parts to remove details not seen at the top level. If this is your top level assembly, you only need the front face of the button. You don't need all the terminal screws. You don't need all the contacts inside of it, everything else. Create a config that's simplified that gets rid of all that detail. We change options on patterns. Use geometry pattern where you can. I've done blog articles about this, and you can cut truckloads of time, thousands of % of rebuild time out of your models by changing your options on your patterns. Remove transparency as well. Adrian showed you in the graphics card options. It has an impact here as well. All those little things are what add up to a lot of information there. So what we got here, When we cleaned up those details, remember, 1/4 of our assembly we cut out on our typical machine. It ran 54.3% faster. On our practical machine, we cut out 22% or almost 23% on that. So it's a big deal. The more details you can remove, the more you can clean those up, the better off you're going to be. You got to remember, a lot of people who put things out on the internet, online, they got summer interns that are going in and modeling their whole catalog of parts, and they're there to make things pretty and to make things as much detail as possible, and it's not always necessary. Save those off in a way that is reasonable for the top level. Keep the detail for the part or for the detail drawings. Yes. The biggest option that I change in patterns is going to be using geometry pattern where I can. Sometimes it's a matter of patterning bodies versus features. If you can pattern a screw that is 5 features, or you can pattern one solid body into different locations, that's a lot less intensive as far as your rebuild and memory use times go. So those are the things that I look out for.
Top-level mates. Now, there are a couple of ways to get top-level mates. Now, the obvious one is to have a whole bunch of sub-assemblies and parts and everything at the top-level assembly, have them all mated together, and have, instead of creating a nice tree-like cascading structure for an assembly. You can get a lot of top-level mates that way. A way a lot of people don't realize that you create top-level mates as well is by using flexible sub-assemblies. To make a subassembly flexible, it has to have calculated the mates so that it can run through its range of motion properly. So it runs everything in a flexible subassembly up to the top level, and then you have to deal with the overhead of that. In this case, we had almost 1,300 top-level mates, the vast majority of those coming from flexible subassemblies that Josh had turned off to run our test. Dropped us down almost 90% to 139 top-level mates.
And I mean, when we talk about, a customer's data set, they are doing all the right things. I mean, when you look at this, seeing 139 mates in there, that's the way it originally started off. Just by turning on that flexible sub-assemblies, that's what's really costing you. Their assemblies are built great, but just one setting in there, it can cost you a huge amount of time.
And it measures out over here in our typical and practical at 13% faster just by reducing those top-level mates and setting that flexible subassembly or those flexible subassemblies to rigid until we actually need to use them and run them through a range of motion. All right? And then 3.4% on your practical, that's not anything to sneeze at. It's faster. And if all you have to do is flip that one switch to get it, might as well.
All right, so the D-feature tool. Once again, we're kind of talking about all the different tools that you can look at in here. D-feature, this can be used on parts or assemblies. It has many different options out there. It is faster than manually modifying the parts, but you have less control over the results. We chose to go with removing internal components on our cab assembly. Remember, we're doing a lot of these performance things on the cab assembly here at the top level, though, and ended up with a part file that was about 400 meg, a couple hundred surface bodies, 1,300 solid bodies is what we ended up with the D-feature tool. And if anybody has used this before or not used it before, you'll see these are the different options that you get in the case of an assembly D-feature. And you can see there's a lot of different controls that you have in here and a lot of different ways that you can set this up. I don't have intimate details of how the customer built everything, so I kind of went with a lot of the defaults and picked and chose a couple different things that I thought were right. And the results that we see up here they're significant. D-feature actually cost us something. It actually made our model run slower, 20.8% slower in the typical and 18% slower in the practical machine. Once again, it's faster, but if you don't have the knowledge of the parts and how they're built, it may actually end up costing you in the long run versus going back and manually modifying the parts like I did originally. So utilizing this. There is a time and a place for it. I would say actually use it on the individual part files themselves as you import them, and I think that's where you get the best bang for your buck with the D-Feature tool. So.
All right, envelopes. And we're trying to see what we can do to simplify the model because we know that simplification of the model is the best way to get higher performance, right? Just as much of that massive calculation out of the model as possible is going to help us out. Envelope's one way of doing that, and it basically, I look at it as a space claim. It's just there to hold the physical space so you know what's there, you know the shape of it, you kind of avoid it if you have to, that sort of thing. It's just sitting in there taking up the space. Now, it's not going to show up on your bill of material. It's not going to show up on mass properties because it's just this dummy void in the middle of everything. But it will serve as a reference so that you can model around it in other assemblies or build things around it. You're not going to measure to and from it or create dimensions off of it, but you'll be able to move around it, reference it visually, that sort of thing. And it can make some pretty interesting improvements. Our typical, it saved us 36%, but on our practical, not so much. Not so much at all. 0.4%.
Yeah, we turned the sub-assembly. There's an option in there to set that as an envelope component, and that's all we did. So this is, once again, it's kind of one of those one-button click things. So it is something that if you're going to be working on a smaller portion of this, maybe fitting up some brackets or something like that to it, you could turn a couple sub-assemblies to envelope and save yourself some time and easily be able to turn those back off again. So, right, we got 15.
Yeah.
Okay. So that's what we're at with that.
Now, large design review, you can look at this as like e-drawings within SolidWorks. It allows you to show, navigate through, build like walkthroughs through an assembly, but you can't do much with it other than that. In fact, it tells you what the limitations are right there on the screen. Assembly features, component patterns, mates. There's lots of things that you can't do to this thing just because you've got it in large design review. It's used to show people what you've done, not do stuff. Okay? In fact, it's so much that way that we can't even run the benchmark on it. You can't, it physically won't happen. You can't touch those buttons. So, use it for what it's used for.
Yeah.
In fact, you can't use it for what it's not used for, so there you have it.
All right, so the next thing we look at here, speed pack. This can be created at the top level assembly or in a sub-assembly to an existing configuration. You can choose faces or bodies to be referenced in other assemblies. So this is an envelope basically with a few more features in it. You can actually grab different faces and bodies to use as reference points. So you got an engine assembly that goes into a top level assembly. You can pick all the mounting points for that, so you can actually mount that thing and mate it into place in your top level assembly, but you don't have all the overhead of everything else inside of there. You do have the option here for a ghost image, where we saw an envelope that kind of had that blue, that ghost image around it. That is an option that you can leave turned on. Once again, I've taken some of the settings that we see inside of SolidWorks. It tells me if I remove the ghost, it's going to further reduce memory. What do you think I'm going to do? I'm going to check the option for remove ghost, obviously. So what we end up with as far as our results go at this is our speed pack ran 67.7% faster in our typical setup. Our practical was 30.7. You can probably see a little bit less than that if you don't use the remove ghost. But it's pick and choose at that point in time. Choose what's going to work best for you, test it out, see what each of those options does for you.
All right. I'm going to go through some of the save as part options. Give Josh a break. His voice gets tired. Yeah. But we're trying to find that best tool for optimizing or for simplifying your model. And just make sure you realize that just because it doesn't work well for us or because it works to a certain level for us, it may be completely opposite for you guys. You got to, in your environment, play with these options a lot and determine what's best for you. You know, defeature didn't do much for us. In fact, it hurt us pretty bad. But there are situations where that is the optimal tool for your use. So make sure you experiment. Experiment around and have some fun with it. All right? Here we're going to do, there are 3 different versions of save as part. The first one we're going to look at is exterior faces. Turned out to be the second best option. We're just taking the exterior faces of this assembly, only those exterior faces, and saving them. Now the resultant of that is we got no solid bodies at all. We just took the faces and nothing else, right? Just the faces. And we got a 79 megabyte part file. So you can imagine that could, you know, come up pretty quick, could rebuild even faster. It's no real intelligence to the model at all, so it's going to be pretty quick. All right? And it is 55.1%, 55% faster on the typical and 21% faster on the practical. It makes an impact in both configurations. That's a pretty good deal. But if we move on to the next option, which is exterior components, and we're saving the components themselves, just the exterior ones, leave everything on the inside out of the picture. Now we got 129 megabytes worth of data, and we have a lot of solid bodies now. We kept the solid information. We got over, almost 1,100 solid bodies and 225 surface bodies to complete this. Now, this was our best option, giving us 60% faster and 26% faster on the practical, or on the practical machine. That's not bad. Yes, ma'am.
Checking your mass and center of gravity. If you were to save things out as essentially a shell, or a shell of what it is, don't you throw your weight and your center of gravity?
Yes, you will. And these methods that we're talking about are to be used generally as design tools, not as your final product and not as your as your final product. What we want you to do is use, we all use configurations to discern from different products that are similar to each other. Maybe 14 different variations of a screw. What we're talking about is possibly using configurations as a modeling management system. And you would have a configuration that would have your representative part in there so that you could model in other areas of your assembly, and then you would turn that back off and bring up your production assembly that you replaced to get your mass properties and stuff. This is a replacement, but not, or a substitution, but you don't replace it for good.
And I get that, but then that begs the other question. If you have several parts, and say, in my company, we do bottom-up design.
Mm-hmm.
All right? So we could have 400 configurations already in one part. And so you build this assembly or whatever, and, it gets really weighty just doing that. So don't you add some weight just by adding configurations?
I see what you mean. If you're using configurations as a way of managing parts and production and that sort of thing, it does add a lot of mass to the files. A lot of mass to the files. And a lot, yeah. When you do, oh, I understand. When you do it this way, it does add some mass. It does add some girth to the files and makes them a little more cumbersome, a little bigger. But the benefit that you get out of it far outweighs that. Okay. The last one, save as part with all components. And we were a little confused by this one. We end up with a file size of 317 megabytes and 3,700 solid bodies with 271 surface bodies. Now, the worst option, we can see how that would happen, but what we can't see would happen is how it would do that to us. 95% slower in our typical and 4.7% slower in our practical. That's just ugly, okay? So we're going to give you the results that we got. I can't explain it. I don't know why it happened, but we did run the test more than once to make sure, and that's what it did to us. Again, it could be different for you. Your environment's different, your models are different, you got a different situation, but for us, it wasn't pretty.
All right, so the next thing that we're going to talk about here is large assembly mode. And what we end up with large assembly mode. This has the greatest impact on performance. Utilizes loading models lightweight, as well as several other system options that are going to generally increase your performance. You can see exactly what it's doing there. You have control over turning those different things on and off, but it gives you an idea of what's going to be happening behind the scenes there. And like I say, this is one of the biggest things, and we recommend people use this over and over again. Lightweight, we've heard in the past people say, there's problems with it, not rebuilding my models correctly. It doesn't indicate when things go out of date. It does. There's settings in there now that make it efficient, and it gives you the indication when things aren't loaded the right way or things need to be updated. So it's definitely something worth using. And you can see here, our typical machine, 81% faster. Our practical machine, almost 60% faster. So just that one thing for loading these things lightweight in large assembly mode, it's a huge difference right there. So, all right.
All right, we are almost done, guys. We got 5 more minutes on the clock, and we are at the grand finale. How's that for timing? We're doing pretty good. What we did was we decided to run the grand finale at the practical hardware, and we set our system up, or our modeling file set up to these options. Real views turned off, image quality set properly, flexible subassemblies are removed, so on and so forth. We fixed a lot of assembly details as well. It made a big difference. So we're doing pretty good here. All right? Why didn't you catch that, Josh? We ran it on the practical. Thank you very much. We ran it on the practical. That should be, and I'm going to say this to make sure the recording picks it up properly. It should be 4.5 gigahertz processor, 4 cores, 16 gigabytes of RAM, the SSD hard drive, not the Revo, and the Quadro 2000 graphics card. Thank you for mentioning that.
That was in your notes. You changed only the header on that one.
It's still your fault.
Okay.
All right, we'll move on.
All right.
So we're going to go to
optimal without large assembly mode. So what happens with our optimal? We're going to our optimal setup without large assembly mode at this point in time. So what we see here is our typical machine. We cut down by almost 66%. And our practical machine, 31.6%. So you can see, bringing everything together, it does start to make a significant difference in your setup and how everything runs there.
So the next step is to see what happens with large assembly mode. Let's do all the changes we've had and throw large assembly mode on top of it as well. We found in the past that large assembly mode is kind of the great equalizer. If you take all that meat out of the assembly, you don't need all that RAM. So that's why we do it in 2 different forms. But if we add large assembly mode into it, this is how fast we can go. Remember, this was 4 hours and 43 minutes and 44 seconds, and we did it in less than half an hour with the right hardware and the right modeling methodologies. Now also realize that when Josh changed the assembly detail, or when he used certain methods to take some of the meat out of the assembly, he only did it in the cab. That's only a small portion of this assembly, so we could have done even better, but we didn't redo all of the model. Okay, just that cab is what we worked in when we were simplifying things. But even in our practical, even when you're already down to an hour and 17 minutes, hour and 18 minutes, under 20 minutes to get it done with the proper hardware. These numbers are huge for productivity in a company. Your time is worth so much more than a $4,200 computer. And when you look at the delta between the typical and the practical, it's even more absurd that you don't have that machine. Your time is worth more than that. All right? Next. We want to say thank you. These companies were a big deal in helping us do this. Racine Railroad is the only customer that had the audacity to help us and give us a model we could show you. And we really appreciate that. That was phenomenal. Last year, we did all of these slides with cartoons of the Roadrunner instead of pictures of the models we used, and they helped us out tremendously. NVIDIA loaned us graphics cards, and Box loaned us machines. So if you could, just go by their booth and tell them thanks too, because that was a big, big help for us. It's a lot of good data here. In fact, you can go to that address right there and download the presentation. Give it a couple of days to get up there. We didn't finish it until a few minutes before this presentation.
And if you want to see the one from last year, just change the 2013 to a 2012. You'll get that one too.
Yeah. So, but we're ready for questions, and it is 25 seconds to 6 o'clock.
That's pretty good timing. All right. Well,
thank
you,
for
everybody.
Questions.